Okay, so I will share my screen. Okay, everybody can see my screen. You can hear my voice.
Yes, sir.
Okay, thank you for the response. Okay, so last week we have learned until this slide. Okay, so we have tried to answer the example 3.1 until example 3.3. Okay, so maybe before we proceed, maybe we can refresh again what we have learned from the previous week. Okay, so last week we have learned about the power calculation for AM. Okay, so the AM that we learned previously is about double sideband full carrier. Okay, so double sideband full carrier, you must know the general equation for double sideband full carrier. So it is VAMT. Okay, it is a function of time which is equal to Vc sine 2 pi fct, okay, plus Vm over 2 cos 2 pi Fc minus Fm. So this is for the lower sideband. Okay, and then minus Vm over 2 cos 2 pi Fc plus Fm t. Okay, so this is for the upper sideband. So we have three components. Here we have the carrier component. Okay, we have the lower sideband, and also we have the upper sideband component. Okay, and if we draw the frequency spectrum for the double sideband full carrier, you will see that we're going to have three components. Okay, so this is V versus F. So this is so this is Fc carrier, this is Fc plus Fm, and then this is Fc minus Fm. So this is Vc, this is Vm over 2, this is Vm over 2. Okay, and the way we want to calculate the total power is by adding all the power component. Okay, all the components power. So P total is equal to Pc, the carrier component, plus PLSB plus PUSB. Okay, so how much is PC? So PC is equal to V square over R, V square over 2R, which is this one. If you see from here, this is PC, V square over 2R, Vc square over 2R, plus PLSB, which is M square Vc square over 4 times 2R. So this MVC over 2, this is equal to Vm over 2. Okay, so MVC over 2, so this is MVC over 2 square divide with 2R. Okay, so you get M square Vc square divide by 4 times 2R, M square Vc square divide by 4 times 2R. And according to this equation, we can simplify the equation by substitute the component with PC. Okay, so if you see from this equation, this is actually a PC component. Okay, so we can rewrite the equation to be P total equal to carrier power plus m square over 4 PC plus m square over 4 PC plus, up till here, and then P total is equal to PC in bracket 1 plus m square over 2. Okay, so after we rearrange the equation, we're gonna get this equation. Okay, so this is only true for AM double sideband full carrier. Okay, this is only true for AM double sideband full carrier. Okay, in general, the total power calculation is like this by adding all the power component. If you have only 3 components, you need to add all of them. If you have 2 components, you need to add only 2, depending on the equation. Okay, before you calculate the total power, first of all, you need to know the complete equation. From there, you know how many components are there in the equations. Then you can calculate the total power. Okay, so we have learned that during the ideal case, even during the ideal case, carrier component consume 2/3 of the total power. Okay, 2/3 of the total power belongs to the carrier. And I've mentioned before that the carrier itself does not carry any information. Okay, the information are contains within the sidebands. Okay, so you see that here the carrier does not contain any information. Okay, and the information only contains within the sideband. And for the case of a double sideband full carrier, the information contains in the lower sideband is the same as the information contains in the upper sideband. It is duplicated. So you can say that as if we send the signal, as if we send the information twice. Okay, seolah-olah macam kita menghantar information itu 2 kali, seolah-olah. Okay, so from this characteristic of the double sideband, you see that if 2/3 of the total power belongs to the carrier, that means both sidebands only consume 1/3 of the total power, and each sideband is half of it, which is 1/6 of the total. Okay, so this is during the ideal case, and during the non-ideal case, this power will be much less than 1/6 of the total power, which is not good. So ideally, we want the sideband power to be as high as possible, because information are contained within the sideband. So we need the sideband to be as high as possible. Okay, so it is said that for the double sideband full carrier, this method of modulation, AM modulation, is inefficient in term of power, in term of power conservation, where it takes a lot of power only for the carrier, whereas the carrier does not contain any information. Okay, so it is said that for certain kind of application, this double sideband full carrier is inefficient in terms of power consumption. Okay, and it is also said that the double sideband full carrier takes a lot of bandwidth compared to the other types of AM, where you see that the bandwidth is equal to 2 times the FM. Okay, and you see that from here we have learned that the information is duplicated both in the lower and upper sideband. So it is also we can say that it is also inefficient in terms of bandwidth requirement for certain kind of application. Okay, so when we say that it is efficient or not efficient, it does not mean that it is not good for all types of applications. Okay, we need to know what is the requirement of each application. Some application requires lower power, some application requires lower bandwidth. So for that kind of application, this double sideband full carrier is considered as not efficient. Okay, and we have gone through example 3.2 and also example 3.3. Okay, we have gone through this example in the previous week. So I will proceed with example 3.4. Okay, so please open your calculator so that we can do together, we can answer the questions together. Okay, okay, so example 3.4, a spectrum analyzer with an input impedance of 50 ohm. So you are given resistance R equal to 50 ohm is used to measure the power spectrum of an AM signal at the output of the preamplifier circuit. Okay, so you see that this is about the spectrum analyzer which want to see the power spectrum of the AM. So the word AM here is referring to the double sideband full carrier. How do I know this? Because this has been stated in the earlier slides of the lecture notes. Whereas if it is said as AM, it is referring to the double sideband full carrier. Okay, so the AM signal has been modulated with a sine wave. So we know that this is a sine wave. So the effective power of the carrier is equal to 745 milliwatt, and each sideband is has a power of PUSB and PLSB equal to 125 milliwatt. Compute the following question. So you are actually given the carrier power, you are given the PUSB and PLSB which is equal to 125 milliwatt. Okay, so if you sketch the total the power spectrum, if you sketch the power spectrum, so my suggestion to all of you, if you get this kind of question, I suggest you to draw on your own so that you can have better understanding of the given question. Okay, so this is F. You can say that this is double sideband. Okay, we can draw this as a power spectrum. That means P versus F. So you are given 745. This is for example milliwatt. So you are given 745, and then here is 125 milliwatt and 125 milliwatt. So this is FC. This is FC plus FM for the upper sideband. FC plus FM. This is FC minus FM. Okay, so when you want to calculate the total power is equal to P total equal to PC plus PLSB plus PUSB. Okay, you need to add all the component plus PUSB. So how much is this? So this is equal to, you just need to add up all of it. So 745 plus 125 plus 125. So you get 995. Okay, 995 milliwatt. Okay. And then what? The peak carrier voltage. So I think this, okay, this has the answer here. Okay. So the peak carrier voltage. Okay. So if you see from here, you can see that, remember the power calculation. Power is equal to V peak over 2R, or this is also equal to Vrms over, sorry, this is square, V square over 2R, or Vrms square over R. Okay, so now the question asks how much is the V peak. Okay, if it is a V peak, that means we can use this equation to find the peak amplitude. Okay, so that means Vc peak square, okay, divide with 2R is equal to the carrier power, which is 745 milliwatt. Okay, so that means Vc peak square is equal to 2 times R is 50 times 750 milliwatt. Okay, and this is equal to, let's try to do this, 100 times 750 milli. Okay, so we get 75. This is a voltage, so this is a volt square, so 75 volt square. So Vc peak is equal to square root of this, so you get square root of 75, so you get, this is 8.66, 8.6603 8.6603 volt. Okay, almost similar with this one. So this is the answer. So you can use peak equations to find the this one. So 750, I repeat again, times 100, so we get 75, and then we need to do square root of answer, so we get 8.6603 volt. Okay, if you want to find the RMS, you can use this one, Vrms square divide with R, equal to 745 milliwatt. Okay, and then what? The question asks the modulation index M and the percentage of modulation index. Okay, so in this case we can use the equations. Okay, since we already know for the double sideband full carrier about the simplified equation, we can use a PT equal to PC in bracket 1 plus M square over 2. Okay, if you don't want to use this equation, that means, okay, if you don't want to use this equation, that means you need to define M equal to Vm over Vc. So you need to find Vm, you need to find Vc. Vc, we can find the Vc. We already know the Vc from the previous this one, which is 8.6603. But we don't know how much is Vm. So Vm can be calculated based on the value of power of the lower sideband or upper sideband. Okay, so either one you can choose, no problem. Okay, so from here, from these equations, okay, we can rearrange the equation, and then we can get M equal to square root of 2 times PT over PC minus 1. So we just need to put inside the values, 995 divided with 745. So both of this is in milli, so we can cancel out the milli. So 995 divided with 745 minus 1, multiplied with 2, and then we do the square root. So we get 0.8192. And if you want to calculate the modulation index in terms of percentage, we need to multiply with 100%. So we get 81.92%. Okay, so this is the modulation index and also the percentage of modulation index. Okay. If you don't understand, please ask question. Okay, boleh tanya soalan. Okay, you are most welcome to ask question. And then what? The modulation voltage Vm. Okay, modulation voltage Vm. So how to find Vm? Okay, how to find Vm? So we can find Vm based on the modulation index, or you can find Vm based on the lower sideband or upper sideband power. So it's up to you. Okay, so let's say we try to find the Vm peak based on the modulation index. So modulation index, remember, Vm over Vc. So this is the peak amplitude divided with the peak amplitude. So Vm is equal to mVc. Okay, mVc. So we take the Vc peak multiplied with m. So we're gonna get V modulating signal peak. Okay, V peak of the modulating signal equal to mVc peak. So we get 0.8192. So this is from the modulation index, and this is the carrier. Okay, so previously we get this one, we get 8.6603. Okay, so this based on this example, it gets 8.6313. So no problem. If you get 8.6603, you just need to multiply it with the value of modulation index. Okay. So if you multiply using this value, so how much we get? Yeah. So 0.8192, if I multiply with 8.6603, so we get here multiply point 8.6603, so we get 7.08. Okay, 7.08 7.0859. Okay. And then what? So this is optional. The question does not ask for this to find the VRMS. The question asks you to find the Vm. So this is they don't specify whether this is a peak value or the RMS value. Okay, normally we ask for the peak value. But if you want to find the RMS value, you can divide the peak value with square root of 2. Okay, you can divide with square root of 2. Okay, so divide with square root of 2. For example, here peak value divide with square root of 2, we get 5 volt. Okay. Okay, even for this one, if you divide with square root of 2, you get 5.01 volt. Okay, so this is how to find the RMS value for the Vm. Okay, so you have question about this, you can ask. Ada soalan yang tak faham, boleh tanya. Okay, no question. So if you don't have question, I will move to the next question, which is find the upper and lower sideband voltage. So upper and lower sideband voltage is equal to VLSB, equal to Vm over 2 for both VLSB and for each of the VLSB and also VUSB. Okay, so you see that VLSB is equal to Vm over 2, which is equal to MVC over 2. Okay, so you can actually take the value from here, from the peak value here, which is 7.078, this one. So let's say that I take the value given here from this example, Vm peak. Okay, so 0.0708. Okay, so 0.0708 divide with 2, so we get 3.5. Okay, 0.0708 divide with 2, so we get 3.53554. Okay, 3 point, yeah, so 3 point, let's say I get this one also, so this is actually, okay, I get 3.5354 volt. Okay, so we already get the value for the VLSB and also VUSB. Okay, so the value here that for this one, this 2.5 is actually the value of effective voltage, which is the RMS voltage. Because if you divide with square root of 2, okay, 3.5354, you divide with square root of 2, you get the RMS value. So this is actually the RMS value. Okay, if you want to find the peak value, you need to multiply it with square root of 2, or you can directly calculate using the Vm over 2 equations or MVC over 2 equation, where for this one we need to use the peak of the carrier voltage. Okay, so the answer is this one. Okay, the peak value. Okay, again, this question does not specify whether this is a peak value or RMS value. Okay, and normally in the test or final exam question, we normally ask the students to find the peak value. Okay, most of the time we ask questions about the peak value. So if you get this kind of question, you can choose either RMS or peak value is okay, no problem. Okay, so if you get this kind of question in the test or final exam, you can choose either one. Either you want to find the peak value or you want to find the RMS value. Okay, one value is enough. Okay, no need to write both values, peak and also the RMS value. Okay, and then what? The next question asks to find the to sketch the waveform that you would see with an oscilloscope if it were placed in parallel with spectrum analyzer. Okay, so in this example, actually we need to find the waveform that we can see from the oscilloscope and compare side by side with the spectrum analyzer. So spectrum analyzer shows the spectrum, okay, frequency spectrum, whereas the oscilloscope in this example shows the AM waveform. Okay, so how to draw the AM waveform? Okay, so in order to draw the AM waveform, so maybe I need to so I can try to draw, where should I draw? Should I draw here? Okay, maybe I can draw here. Actually last week I already taught you how to draw the AM waveform. So when you want to draw the AM waveform, okay, what I want to see actually, you draw correctly and you label correctly. Okay, if you remember in the previous week I taught you how to draw the AM waveform. So when I want to draw, first of all I will draw the imaginary line. This one, this is actually equal to VC, and also the minus VC level. Okay, sorry. And then I draw the AM waveform. Sorry, I draw the imaginary line of AM waveform. Okay, imaginary line of AM waveform. Okay, this is just imaginary line, and then I can draw the AM wave. Okay, so and then what? So I draw correctly, and I need to label. So I need to label that this is V versus time. First I label the axis, and then I label the peak amplitude and also the maximum value, and also the V minimum. So this is the maximum. The maximum is equal to Vmax equal to VC peak plus Vm peak. Okay, so 8.6313 plus 7 point how much? 7 point let's say we use the same value. Let's say we use the same value, 0.70808. Okay, so this is 8.63 plus 7.07. Okay, 7.07. Okay, so what happened, I don't know, sorry. V min is equal to VC minus Vm. Okay, VC minus Vm. So we get the value equal to 1.5603. Okay, so the peak Vmax is equal to 15.70. 15.7023. Okay, so I need to put the value over here. So this is a 15.7023. This is for the maximum, and then for the minimum is this one is 1.5603. Over here is minus 15 point. Minus 15.7023. This is the lower side for the negative at the negative part, and this is negative 1.5603. Okay, so this AM waveform has the positive and also the negative values. So I draw correctly, I label the axis, I label the maximum and minimum, so this drawing can get full marks. Okay, boleh dapat full mark untuk drawing seperti inilah. So you don't need to use calculator to draw the AM. Sorry, you don't need to use ruler to draw the calculator. Okay, jangan guna pembaris untuk melukis AM waveform, because this will consume a lot of time. So you're going to waste a lot of time just to draw a simple waveform like this. Okay, so be careful about that. Okay, time is very crucial, especially during the test and final exam. So you must make sure that you draw quickly. Okay, so that's for this example 3.4. Example 3.4, you have question to ask. Ada soalan tak nak tanya?
No, Doctor.
Okay. Boleh So kalau tak ada soalan, if you don't have question, I will move to the next example. Okay. Okay, tak ada soalan So I'll move to this to the next topic which is modulation by several sine wave. Okay. So this has been asked in the previous semester's test and also the final exam. We have asked we have asked question about this topic in the previous semester. Okay. So what is modulation by several sine wave? So in this topic, it is actually like this. So imagine that we have the imagine a modulator in the transmitter. Okay, a modulator in the transmitter. So this transmitter receive the carrier VCT. Okay, and we already know that the input here is VMT. Okay, actually we can have many inputs message. VM1T, VM2T, VM3T, VM4T, and so on. Okay, we can have many input and one carrier. So one carrier carries many input message together. That means as if we do the multiplexing, okay, using the modulation process. Okay, so in order to do this, okay, so how can we find the V total? V total here is the total voltage of the message, which is equal to V1 square plus V2 square plus V3 square and until Vn square and then square root. Okay, and if we want to find the modulation index, we need to divide the peak amplitude of the input message with the carrier voltage. Okay, so now we want to calculate the total modulation index. So in order to do that, we need to find the this one, V total over Vc, which is equal to V1 over Vc square. So this is for the first message plus V2 over Vc square for the second message plus V3 over Vc square until Vn over Vc square. Okay, so this is actually M1, M2, M3 until M of n. Okay, so you see that we get M1 square plus M2 square plus M3 square until Mn square and then square root. So we get the total modulation index. And from here we can calculate the total power, which is for the double sideband full carrier, which is equal to PC in bracket 1 plus M square over 2. Okay, so this equation is also true for the double sideband full carrier with many input message. Okay, so you see that in the previous semester, how does the question looks like? How does the question looks like? Okay, so in the previous semester we have given the student questions with the question gives the student the carrier. Okay, the carrier equation VCT. Okay, which is with some value, which is Vc sine, for example, Vc sine 2 pi fct. Okay, so in the test or exam we give the values. Okay, for example what 5 sine 2 pi and then multiplied with the carrier, for example 1 megahertz times t. Okay, so we give the value. So here for this example, I just put the variable so that you can have a picture on how the previous question looks like. So if you have time, please browse through the question banks, okay, to look into this kind of question. And then we also give the input, the input message, which is mt equal to so we give a Vm1 sine 2 pi Fm1 t, and then plus Vm2 sine 2 pi Fm2 t plus this is Vm2, and then Vm3 sine 2 pi Fm3 t. Okay, so you see that from here we can find the modulation index. Okay, so this is a V1, V2, and also V3. So in order to calculate the total modulation index, that means M total is equal to square root of, in this example, that means Vm1 over Vc square plus Vm2 over Vc square plus Vm3 over Vc square. Okay, so we get the total modulation index. Okay, and how does the spectrum looks like? Okay, how does the spectrum looks like? So if you get this kind of question, remember, for the double sideband full carrier, each input will produce two sideband. Okay, remember previously we have one carrier, one input message, and it produces two sideband, double, and a carrier. Okay, so imagine if you have a 3 input, that means we're gonna have 6 sidebands. Okay, we're gonna have 3 pairs of sideband, which is 6 sideband, 3 upper and 3 lower. Okay, so if you want to draw this kind of question, that means it looks like this. It looks like this. For example, this is a V versus F, and for example the carrier is here, for example. Okay, so the carrier is here, carrier as usual, Vc. Okay, and then we have the first input message. Okay, the first input message. So this is, for example, at how much is this? Fc plus Fm1, Fc minus Fm1. Okay, and this is how much of Vm1? Vm1 over 2. This is Vm1 over 2. And we have another one, okay, depending on the value of the amplitude. So let's say that the value is lower, for example. Okay, so this is Fc plus Fm2. Okay, and here is Fc minus Fm2. Okay, and the value is Vm2 over 2, Vm2 over 2. Okay, and the other one is, for example, here located at Fc plus Fm3. Okay, and another one here is located at Fc minus Fm3. Okay, and the value of the amplitude is Vm3 over 2, Vm3 over 2. Okay, and you can also calculate the total power. So now the total power, you can use this equation, since we are using double sideband full carrier. You can use this simplified equation, or so this is true for the double sideband full carrier, even if you have many input. Okay, even if you have many input. Okay, you can use this for this kind of example. or you can find based on the component. So we have P total is equal to we have the carrier plus P LSB 1 plus P USB 1, okay, and then plus P LSB 2 plus P USB 2 plus P LSB 3 plus P USB 3. So we have 7 component, 6 sideband plus 1 carrier component. So we get the value of total power. How much is power? Power is this one. For example, this one. Okay, when you want to find the power, that means this is Vm over Vm1 over 2 square divide with 2R. Okay, divide with 2R. So you get this power. Similar with the other components. Okay. So yeah. So from here, you know, remember, if we have more than 3 inputs, for example, if you have 10 inputs message, for example, then we're gonna have 20 sideband, 2 times. Okay. So what about the bandwidth for this kind of example? If we have 3, if we have 3 input message, because this has been come out in the previous semester, so I explain here. So for this kind of example, if you have 3 input message, that means the bandwidth is until FM3. So you see that the distance here is until FM3. Okay, so the distance is 2 times. So that means that the bandwidth is equal to 2 times FM3. So in this case, FM3 is the further away, the largest input message frequency. So this is 2 times FM3. Okay, the highest input message frequency. Okay, so go back to this slide. Okay, so we know that we use the total modulation index. So I proceed with the slide. Okay, so we know the total power. If we know the total modulation index, we can calculate the total power using the simplified equation. Then you see that we already know this, and then here we can also change the power into currents. Okay, so P total is equal to I total square multiplied with R. Remember the power equation, power is equal to I square R. Okay, I total square R equal to IC square R multiplied with 1 plus M square over 2. Okay, rearrange the equation, so we get IT over IC, okay, equal to square root of 1 plus M square over 2. Okay, and if we want to consider multiple input, that means we need to use total modulation index square over here. Okay, so okay, if you want to ask question, you are most welcome to ask question about this, or else I will proceed with the next slide. Saya akan teruskan. Okay, antenna of okay, example 3.5. So this example, the answer is actually wrong here. So okay, we can discuss about this. Example 3.5. The antenna of an AM transmitter is 8 ampere when only the carrier is sent, but it increased to 8.93 ampere when the carrier is modulated with a sine wave. So it said that here, imagine a transmitter system. Okay, so transmitter receive the carrier. Okay, so it is said that when there is no input message, only carrier is sent. So the power here is 8 ampere. okay, power to the antenna. And when there is an input over here, okay, and when there is input over here, the current increase to become 8.93 ampere. Okay, so what does it means? Okay, what does it means? That means when there is no input, that means it is the current is actually referring to the carrier current, IC. And when there is a input message, there going to be modulation process. So that means this is referring to the total current, I total. Okay. So find the percentage of modulation. Okay, there are two questions here. The first question is find the percentage of modulation. Okay, so how to find that percentage of modulation? So you can use this equation, IT over IC. Okay, IT over IC. Okay, this equation. So that means IT over IC equal to square root of 1 plus m square over 2. Okay, this equation. Okay, so this one we can calculate this one. So IT over IC, how much is this? So 8.93. So you see that here, 8.93 divided with 8 equal to square root of 1 plus m square over 2. Okay, so that means 1 plus m square over 2 is equal to so 8.93. So use your calculator. 8.93 divide with 8 and then square the answer. So 1.246. So 1.246. Okay, so m square over 2 is equal to 0.246. Okay, and then m square is equal to 0.246 times 2, 0.492. So m is equal to square root of answer, you get 0.701. Or in terms of percentage, we get this one is in terms of equal to 70.1. So this is 1/4. So 1/4%. Okay, so it is not supposed to be 100%. So this is actually wrong. It is not supposed to be 100% because this is not I message, it is a I total. So I total is larger than the carrier power. Okay, so you can use the based on the power calculation, power equations, which is IT over IC. Okay, what's next? So the next question asks, okay, the next question, because this is N, so there are two questions here. Okay, ada dua soalan di sini. So the next question asks, find the antenna current, the current supplied to the antenna. Okay, find the current supplied to the antenna when the percentage of modulation change to 0.8. So what if this value of m becomes 0.8? How much is the current supplied to the antenna? Current supplied to the antenna means that I total. Okay, you need to find the I total. What about IC, I carrier? I carrier is still the same, which is 8 ampere. Okay, 8 ampere, still the same with the previous one. Okay, so therefore I total is equal to IC IC in brackets square root of 1 plus m square over 2. Okay, so we can use this one. So this one is 8 square root of 1 plus 0.8 square divided with 2. Okay, so this one is okay, so 0.8 square divided with 2 plus 1 and then square root of answer. Okay, so I get here is 8 multiplied with 1.1489. Okay, 1.1489. So this is 8 multiplied with 1.1489. I get 9.19121912 ampere. Okay. Okay, try to use your calculator. Can you get the same answer or not? Okay. So this question is actually one to test you, to ask you what happened to the current if we increase the modulation index. So if we increase the modulation index, that means the current also will increase. Okay, so the higher current triggers the higher current produce the higher modulation index. Okay, so this question wants to show you the relationship of current increment values, okay, with respect to the modulation index. Okay, so if you have question about this, please ask question. Boleh tanya. Okay, you are most welcome to ask question. If you don't understand, please ask question. If you don't ask, that means I assume that you understand. Okay, and I will move to the next slide. Boleh Kalau tak ada soalan, saya teruskan. Okay, so previously we have seen AM about double sideband full carrier. So there are actually many other types of AM. Okay, because we have learned previously double sideband full carrier is actually the oldest technology of AM. There are many other types of AM, okay, which is a AM family member. Okay, so we have here is the double sideband suppressed carrier. Okay, so the word suppress means that we reduce completely the carrier power. And then a double sideband reduced carrier, so we reduce the carrier component for certain amount of percentage. And then single sideband, that means only one sideband. Okay, only one sideband with carrier or without carrier. Okay, so here is consists of two, with carrier or without carrier. Okay, or without carrier. Vestigial sideband is used for the TV broadcasting, which carries the video signal and also the audio signal. Okay, you're going to see about VSB that the amplitude of the sideband is not equal, and the distance of sideband from the carrier is not equal. It's not like the double sideband full carrier. So vestigial still carries two sideband, okay, but the sideband amplitude is not equal. Okay, upper and lower is not equal. And about the bandwidth, the distance of the upper sideband and the carrier is not the same as the distance from the lower sideband to the carrier. So the bandwidth is not 2 FM. Okay, the bandwidth is less than 2 FM. Okay. So how does the spectrum looks like? So actually we're gonna go through one by one about this. Okay, we're gonna go through one by one about this. Okay, I will explain later about this. Okay, so we go through the first one. Okay, through the first one. power content of the double sideband suppressed carrier. So I skip this one because you don't need to memorize this. You don't need to memorize this because we're gonna go through the total power later. So you don't memorize the equations. Okay, let's go through the example of this, the waveform. From here, you will have more understanding about the calculations, about the parameters, about the important parameters. Okay, so this is double sideband suppressed carrier. So the word suppressed carrier means that we suppress completely the carrier component. Okay, so the word suppress here, you can assume that we eliminate the carrier component, but it is not eliminate actually. It is not like we remove. When we suppress the carrier component, you will see later that the power or the voltage will be distributed to the sidebands. So the sidebands amplitude will become increased compared to the double sideband full carrier. So how does it possible? So mathematically it is possible. Okay, mathematically, which is the theoretical concept, it is possible. Okay, we're gonna see about the equation later. Okay. So you see that the first graph here is the carrier, which is the VCT, and then here this one is VMT. Okay, and here is VDSB SC. Okay, this one. So this is the waveform, and then the last one is the amplitude spectrum. Okay. So you see that the waveform almost similar, okay, almost similar to the double sideband full carrier. But there's an important there's an important things happen here in the waveform. You see that at this part. So you see that whenever the input message cross the zero axis, something will happen. Okay, something will happen. Every time the VMT cross the zero axis, something will happen at the output. What is that something? Okay, so this is this thing. Okay, this is what we call as phase shift, perubahan fasa. Okay, this is what we call as 180-degree phase shift. Okay, so the wave at the output change in terms of phase for about 180-degree. It's like an inverse. It becomes inverse actually. So I will explain to you how to draw the waveform later. Okay, after this. And then let's look at the spectrum. So this is a power spectrum. Doesn't matter. Previously we have seen about amplitude spectrum, which consists of voltage. So remember, for frequency spectrum consists of two types. Amplitude spectrum, which is V versus F. Another one is power spectrum, which is power versus frequency. Okay, so for double sideband suppressed carrier, you see that the carrier component has been suppressed. Okay, so the term suppressed here, so initially we have the carrier like this. Initially we have the carrier. When the carrier is suppressed, what happens is that the power is distributed to the upper and lower sideband, and the power becomes increased at the sidebands compared to the double sideband full carrier. So you see that from here, in terms of amplitude, it is not equal to Vm over 2 anymore. Okay, remember, the amplitude of a double sideband suppressed carrier for the sideband is not equal to the Vm over 2. Okay, remember this is not Vm over 2. Okay, when we draw the amplitude spectrum, it is not equal to Vm over 2 anymore. So how much? We don't know. It depends on the equation. Okay, remember the value depends on the equation. We cannot say that this is Vm over 2. Okay, I repeat again, the sideband amplitude is not equal to Vm over 2 like in the full carrier. Okay, so theoretically it is said that when the power when the carrier component is suppressed, the power or the voltage will be distributed to the sideband, and the sidebands becomes increased. Okay, how does it possible? We're gonna see later about that. Okay, so when you want to calculate the total power, that means the total power is equal to PLSB plus PUSB. Okay, so this is actually equal to VLSB square divided with 2R plus VUSB square divided with 2R. So you get the total power. So in this case, you cannot use this equation anymore. PT equal to PC and then square root of 1 plus m square over 2. You cannot use this equation anymore because this is not double sideband full carrier. Okay, don't use this equation. This is only true for double sideband full carrier. Okay, you need to use the general equation like this. Okay, so be careful. So how can we find the equation for double sideband suppressed carrier? So the equation is actually like this. So V dsB SC function of time is actually equal to VCT multiplied with VMT. Okay, so if I elaborate the equation, so this is VC sine 2 pi FCT multiplied with Vm. So I erase this one first. Okay, saya padam je. So this is a Vm sine 2 pi F. So it becomes like this. Vc Vm. Okay, Vc Vm. So because this is sine and sine, sine and sine. So you see that this is sine 2 pi F Ct sine sine 2 pi F t. Okay, so sine and sine according to trigonometry identity will become cos minus cos. So it becomes like this: Vc Vm over 2 big bracket. Okay, maybe I don't need to use big bracket. Wait, Vc Vm over 2 cos. Okay, cos 2 pi. This is lower sideband, which is Fc minus Fm t minus because sine. Yeah.
Mak Dr. macam ada question.
Boleh ulang balik? Can you repeat the question? Apa yang tanya tadi
Doktor,
ya?
doktor punya mic bising lah.
Oh, iya ke? Sekarang macam mana? Masih bising lagi Anybody boleh respon?
Ada sikit lagi.
Oh, masih ada bising lagi Sekejap macam mana
Ada noise.
Ada noise lah, lama. Sekejap. Wait.
Okey, doktor.
Since when ada bising? Sejak bila ada bising?
Baru-baru juga.
Baru. Macam mana sekejap maybe I will go out first and then I will come back So sekejap wait for a while. Okay. Is it clear now?
Yes.
Okay. And no noise?
No more.
Okay, thank you for the response. Okay, sorry for the technical issue So I will share again my screen. Okay, can you see my screen? Can you hear my voice?
Yes, doktor.
Okay. So where should I repeat? Should I repeat the equation of this one? The left equation?
Boleh, doktor.
Boleh So I erase again sorry, tak boleh erase pula. Sekejap. Wait for a while. I try to. Is it possible to delete? Oh, if I want to delete, I will delete everything. So okay, never mind. No need to delete. Maybe I can explain. So okay. I try to find the double sideband suppressed carrier equation. Okay, I try to find the double sideband suppressed carrier equation by multiplying the carrier with the message signal. So VCT multiplied with VMT. Okay, so therefore I define the equation. It becomes like this. So VC sine 2 pi FCT multiplied with Vm sine 2 pi Fmt. Okay, so it becomes Vc Vm sine 2 pi Fct sine 2 pi Fmt. Okay, so this is how we want to define the double sideband suppressed carrier equation, V DSBSC T. Okay, so if I elaborate the equations, so sine and sine, according to trigonometry identity, it will become cos minus cos. Okay, so VC Vm cos 2 pi Fc minus Fmt minus VC Vm, okay, VC Vm over 2 cos 2 pi Fc plus Fmt. So we get the lower and upper sideband without the carrier component. So there's no carrier component in this example. Okay, in the suppressed carrier, the carrier component has been suppressed completely. Okay, and from here, if you draw the spectrum, okay, if you draw the frequency spectrum, so the carrier has been suppressed completely, Fc, and this is Fc plus Fm over here, for example. Now here is Fc minus Fm. Okay, Fc minus Fm over here, for example. So if you draw the amplitude, becomes like this. Okay, so the amplitude here is Vc Vm over 2. So here is Vc. So here is Vc. Okay, Vc Vm over 2. Okay, and when I want to calculate the total power, so total power from this example, okay, you see that P total is equal to Vc Vm over 2. Okay, Vc Vm over 2 divide with this is square over 2r. So the amplitude square divide with 2r, and then plus Vc Vm over 2 divide with 2r. This is square. Okay, so you get the total power. So you see from what I've drawn here, the sideband is not equal to Vm over 2. It is larger than Vm over 2. Okay, lebih besar daripada Vm over 2. Okay, so in order to know the spectrum, we need to know the complete equation first. Be careful about that. We need to know the complete equation first, then we can draw the spectrum, the frequency spectrum. Then we can find the total power. So without the complete equation, we cannot simply assume that it is Vm over 2. Okay, based on the previous semester experience, student did Vm over 2, which is wrong. So be careful about that. Okay, so this is double sideband full carrier. So actually I want to show you how to draw this one, how to draw the waveform. Okay, how to draw the double sideband full carrier waveform. Macam mana nak lukis? Okay, wait Ini kalau nak salin boleh Kalau tak sempat salin, if you unable to write down the notes that I wrote here, you can see the YouTube video later. Okay. So the thing is, students, you need to understand first. Don't waste your time to write everything now. What you need to do now is to understand. Okay, kamu perlu faham dengan jelas. So now I want to show you how to draw the double sideband suppressed carrier waveform. Okay, so when you want to draw the waveform for double sideband suppressed carrier, again, when you want to draw, first we're gonna see that whether you draw correctly and whether you label correctly. Okay, so when I want to draw the suppressed carrier, double sideband suppressed carrier waveform, I will do like this. First, I will do the imaginary line of sine wave like this, and then I will do inverse sine wave imaginary line like this, just for my reference. Okay, and then what? Now I will draw. Okay, so this is actually V versus F. Okay, so this is so I will draw like this. So what happened now? So instead of going down, instead of the wave going down, it will the wave will change the phase for 180 degree. So instead of the wave going down, it will go up like this. And for example, I stop here. So instead of going up, it will be phase shift 180 degrees, so it will go down like this. Stop, and then instead of going down, continue, it will inverse upwards. Okay, so what happened here is actually the 180 degree phase shift. Okay, over here is 180 degree phase shift. Okay, over here is 180 degree. Okay, you understand? Boleh faham eh? So do you need me to repeat again about this, how to draw? If not, I will proceed. Boleh eh? Any response? Okay. So when you want to draw this, make sure that you show the phase shift. Make sure you show the phase shift happens. Okay, make sure you show the phase shift. So again, if you want to, so you see that, for example, I repeat again, I simplify like this. So I draw like this, and then I stop. So here I need to show instead of the wave continue as usual, it will go up like this. Okay, so you need to show this part, which is the 180 degree phase shift. Okay. Okay, so if you don't have question about the wave, how to draw the wave, please make sure you try yourself how to draw correctly without using a ruler. Okay, so you need to practice this one, okay, so that you can draw smoothly during the exam and in a short period of time. Okay, and then what? So I continue again. Advantage of double sideband suppressed carrier compared to AM, compared to double sideband full carrier. So what is the advantage of suppressed carrier compared to the full carrier? First, it is power conservation. So it can it consume a small amount of power. Sorry, the total power, we can save the total power by suppressing the carrier component, because carrier does not carry any information. Okay, carrier does not carry any information. So if we suppress the carrier, that means we manage to consume the power, we reduce the power consumption, especially for the carrier component. Okay, remember the total power is equal to PLSB plus PUSB. Okay, and then easy to generate. Okay, so what is the disadvantage? Rarely used because signal is difficult to recover at the receiver. Requires carrier insertion and complex circuit design. So the circuit design for the receiver is complex compared to the double sideband full carrier. And then take the same bandwidth as AM not efficient. In terms of bandwidth, still the same. Bandwidth is equal to 2 FM. Okay, why? So if you see from here, from this picture, okay, the distance of upper and lower sideband is FM and FM. So it is 2 FM. Okay, in terms of bandwidth, still the same. Okay, so in terms of bandwidth, same as full carrier. So it is not efficient for certain kind of applications. Okay. And then what? Single sideband. Single sideband. So single sideband consists of two types, either single sideband with carrier or single sideband without carrier. Okay. So if you see the first one, single sideband, which is this one, single sideband with carrier. That means we're going to have one sideband and one carrier. Okay. So the sideband we can choose either upper or lower sideband. We can choose. We can choose either upper or lower. Okay. So see that here is the carrier. This is the modulating signal or the message signal. This is the VSSB with carrier. And if we see the spectrum, okay, the spectrum. So this is the carrier. Okay, this is the carrier. And then we have the upper sideband FC plus FM. Okay, and then we don't have the lower sideband, so there's no lower sideband. Okay, so in this case is a single sideband with carrier. So in this example it use upper sideband. Actually you can choose lower sideband if you want, no problem. Tidak ada masalah kalau nak memilih lower sideband. Okay, but for this example it uses upper sideband. Okay, so therefore if you see from here, the total power is actually equal to PC plus PUSB in this example. Okay, so again the sideband amplitude is not equal to Vm over 2. Okay, it's not equal to Vm over 2. So this is Vc square over 2R. This is VUSB square divided with 2R. Okay. What about the bandwidth? The bandwidth now becomes half. Okay, half of double sideband full carrier. Okay. So when you want to draw the spectrum, okay, that means amplitude spectrum. So the graph shown here is a power spectrum. If you want to draw the amplitude spectrum, which is V versus F, so that means we have the carrier, okay, and also the upper sideband, right? VC FC plus FM. So this is VC, this is VUSB, which is not equal to Vm over 2. So what's the value? The value depends on the equation. Okay, the value depends on the equation. Normally when we want to generate the single sideband, first of all we need to generate the double sideband suppressed carrier, and then we need to filter out which sideband that we want so that we can produce the single sideband. Okay, so that one gonna be shown in the next slides. For the next slide, there's an example, there's a notes about how to generate the single sideband. Okay, and then what? Single sideband without carrier. Okay, so you see that this is the carrier, this is the message signal, this is the single sideband wave without carrier, and this is the power spectrum. In this example, it uses the upper sideband. Okay, for example, here is the carrier, this is the here is lower sideband, so we have FC here and also FC plus FM. This is FC minus FM. Okay, and the amplitude here is actually VUSB, not Vm over 2. Okay, bukan Vm over 2. So how much is the total power in this example? That means P total only consists of one component, which is P USB. Okay, which is equal to V USB square divided with 2R. What about the bandwidth? Bandwidth is half of the full carrier, which is FM, which is the distance from sideband to the carrier. Okay, and if you see that the sideband power, the sideband power and also the sideband voltage is larger than the sideband of the full carrier. Okay, so we're gonna see about this example later. Okay. Okay, this one. So this example shows about the theoretical concept of suppressing the carrier component, where the suppressed power distribute to the sideband power. That means when we suppress the carrier, the power will be distributed to the sideband and the sideband power become increased. So how does it possible? And this have been explained mathematically. If I go back a few slides, okay, if I go back a few slides, you see that when we suppress the carrier, mathematically we actually can increase the amplitude of the sideband, which is become VCVM over 2. Okay, so mathematically it can be shown that the sideband becomes increased, not Vm over 2 anymore. Okay, so in this example, in that example 2.9, okay, this one to show what happened when we suppress the carrier. But what happened here is that the carrier is not suppressed completely, it is suppressed for only 90%. Okay, so let's go through the example 2.9. So for a total for 100 watt of total available power in the sidebands, okay, so the word here total, that means this is P total. Okay, compare the power in the sidebands when the modulation is standard AM. So this is actually AM system, which is double sideband full carrier, okay, which has the modulation index 100%, which is ideal case. So we need to compare double sideband full carrier during the ideal case with the double sideband suppressed carrier, where 90% of the carrier component has been suppressed. Okay, that means what? That means initially like this, so I draw again, I draw here so that you can have better understanding on what happened. So initially we have this one, double sideband full carrier, okay, and then these we need to compare with suppressed carrier. Okay, without the carrier component. Okay, but in this case, sorry, it's not without the carrier component, sorry. So the carrier has been suppressed for about 90%. That means there is a small carrier component which is 90% suppressed. Okay, 90% suppressed. And according as what we have seen previously from the equation, theoretically when we suppress the carrier component, the power will be distributed to the sidebands. So the sidebands becomes increased. Okay, so the 90% that we suppress is distributed to both sideband. Okay, the 90% of power of the carrier that we suppress is distributed to the sideband's power. Okay, so let's see in this example. So this example contains two questions actually. First, compare, and then it asks how many times greater is the sideband power in the suppressed carrier case. The second question asks how many times greater. Okay, so let's go for the first question. We compare in terms of sideband's power. Okay, so you see that here during the ideal case, so this is actually a subscript of T, small of T. This is a subscript of C. So this is actually PT and also PC. Okay, again this is also PC, a subscript of C. Okay, so during the ideal case, PC, so this is a PC. During the ideal case, M equal to 1, PC is equal to 2/3 of the total power. That means the sideband power is the remaining, which is 1/3 of the P total. Okay, how much is P total? P total is 100 watt. So carrier power 2/3 of 100, 2/3 of 100, you will get 66.7 watt for the carrier, and the remaining for both sidebands is equal to 33.3 watt. So 100 minus the carrier, so we get 33.3 watt for both sidebands. Okay, so this is for the double sideband full carrier. What about double sideband suppressed carrier, the DSBSC? So double sideband suppressed carrier, it is said that 90% of the carrier power is suppressed, and that 90% is distributed to the both sidebands. Okay, so we need to know how much is the 90%. So 90% of the carrier power is actually equal to 60 watt. Okay, so 60 watt is reduced, but the term reduced here theoretically means that we distribute to the sideband. That means the sideband power becomes increased in the suppressed carrier. So that means the sideband power for in the suppressed carrier case, so initially is 33.3 in the full carrier. Now we need to add with the 90%. Okay, so the sideband power in the suppressed carrier case, it is equal to 33.3 plus 90% from the suppression, so it becomes 93.3 watt. Okay, so you see that here the sideband power in the suppressed carrier is higher compared to the sideband power in the full carrier. Okay, so this is the comparison. Okay, we compare in terms of sideband power. So what about the carrier power? So carrier power in this case for the suppressed carrier, it becomes 10% only. So 66.7 minus 60. Okay, 66.7 minus 60. So we get 6.7 watt only, small. Okay, so you see that now the sideband power is higher compared to the carrier power in the suppressed carrier case. Okay, so now we go to the second question. It asks how many times greater is the new sideband? Berapa kali ganda lebih besar sideband power pada suppressed carrier compared to the full carrier? Okay, so in order to compare, we need to divide the power into ratio. So power sideband new divide with power sideband old. So 93.3, the new power sideband, divide with 33.3. So it's actually 93.3 divide with 33.3. Okay, so you get 2.8. Okay, around 2.8. And 2.8 you can express in terms of decibel, 10 log 2.8, so you get 4.5 dB. Okay, 4.5 dB increment. Okay, there's a 4.5 dB increment in the suppressed carrier case. Okay, so this means that AM info transmitted only 33.3%. Okay, in double sideband full carrier. Okay, double sideband full carrier, we use 33.3% of the power to transmit the information, whereas for the double sideband suppressed carrier, we use 93.3% we use 93.3% of the total power to transmit the information. Okay, so remember, theoretically we want the sideband power to be as high as possible. Okay, secara teoretikalnya kita inginkan sideband power ini sebesar yang mungkin, because sideband contains information, so we need the information component to have power as high as possible. Okay, so that it can reach the receiver with adequate amount of power received at the receiver, because when the signal travels, it will attenuate. Attenuates will reduce the amount of power. So if we can increase the power from the transmitter for the information, that means we can increase the possibility of received power at the receiver, which is good. Okay, so do you have question about this? If you have question, please ask. Okay, if you don't have question, I will move to the next example. Okay, ada soalan? Ada soalan boleh tanya ya. Don't be shy, don't be passive. No problem, boleh tanya.
Betul.
Ada nak tanya soalan ke apa? Ada noise lagi ke?
Doktor ada noise balik.
Alah. Okay, jap. So maybe jap I don't know what happened aja. Wait, I stop sharing first. Oh yeah, I have noise again. I'll stop sharing. Wait for a while. Maybe I need to wait. Okay, now it's better. Is it better now?
Yeah, Doctor.
Okay. So, yeah. So, any question for, sorry, wait, wait. So, I will share my screen. Okay, can you see my screen? Can you hear my voice? Any response?
Doctor.
Apa dia?
Macam mana 67 watt tu untuk apa ya?
Yang mana?
Yang PC equal to 66.7 minus 6 minus 60 equal to 6.0.
This one Okay. So, okay, in the suppressed carrier case, we suppress the carrier power for about 90%. Okay, so that means initially we calculate for the double sideband full carrier, we get 66.6. So I repeat again from the full carrier. So in full carrier, during the ideal case when M equal to 1, modulation index is 100%. So based on the equation of this one, total power P total 1 plus M square over 2. Okay, sorry, this is PC, this is PT. Okay, PC and PT. So when the modulation index is 100%, PC is 2/3 of the total power. Okay, whereas the sideband power is the remaining, which is 1/3 of total power. So how do I get 66.7? 66.7 is from this one, PC is 2/3 of the total. So the total power given in the question is 100 watt. So 2/3, so 2/3 of 100. So you get 66.7 watt. Okay, so this is for the full carrier. Okay, and for this one, that means the sideband, this is PC, so PC. For the sideband power becomes 100 minus 66.7, which is 33.3 watt for the full carrier. Okay, now when we go to when we have the suppressed carrier, double sideband suppressed carrier, the question said that 90% of the carrier power is suppressed. Okay, so 90% of the carrier power is suppressed means that 90% multiplied with 66.7 watt. So 60, which is equal to 60. Okay, wait, which is equal to 60. So 60 watt has been suppressed. Okay, 60, this 60 watt is the suppression. We suppressed 60 watt. Or you can say that we remove 60 watt. Okay, so that means, so look at the picture above here. Okay, so the carrier component becomes only 10%. 10%. So how much is 10%? So 10% is actually equal to 66.7 minus 60. 60 is the suppression, 90% suppression. So I get 6.7 watt for the carrier in the suppressed carrier. Okay, so and then what? As I mentioned previously that when we suppress the carrier component, theoretically the power will be distributed to the sidebands. So that 90% suppression is given to the both sidebands. So the sideband becomes increased. So initially, the sideband power, okay, we get 33.3 based on the previous this double sideband. So initially we have double sideband, and then we suppress 90%. So initially 33.3% of the total, 33.3% of the sideband power now become increased. So we add another 60 watt, which we get from the suppression of the carrier. So the sideband power increased to become 93.3 watt. So this 93.3 watt belongs to the sideband power for the double sideband suppressed carrier case. So you see that the sideband increase in terms of power for 90% increment. Okay, and then the question asks, how many times greater is the sideband power compared to the suppressed carrier case? So in order to compare, we do the ratio. That means power sideband new divide with power sideband old. The new sideband is 93.3, which has been increased from the carrier suppression, and then we divide with power sideband old. Power sideband old is from the previous one, which is from the full carrier. We get 33.3. So 93.3 divided with 33.3, we get around 2.8. Okay, we get around 2.8. 2.8 is if we express in terms of decibel. So 10 log 2.8, we get 4.5 decibel. Okay, so therefore, in the conclusion, this means that double sideband full carrier only transmit information with 33.3% of the total power. In double sideband full carrier, only 33.3% of the total power belongs to the sideband. Whereas for the double sideband suppressed carrier, 93.3% of the total power belongs to the sideband. So we can say that double sideband suppressed carrier is better in term of total power, because most of the power contains in the sideband. Remember, theoretically we want the sideband power to be as high as possible so that we can transmit the signal in a long distance to the receiver. Okay, we need the sideband power to be as high as possible because information are contained within the sideband. Okay, the higher the sideband power would be better. Okay, so compared to double sideband full carrier, where only 33.3% of the total power belongs to the sideband, which is very small, and the carrier has very high power, where the carrier does not contain any information. Okay, you see that here 33.3 33.3% only, okay, belongs to the 33.3 is for both, for both. Sorry, not each of it. Okay, 33.3% for both sideband. So both of these okay, where for the suppressed carrier we get 93.3% for both sidebands. So the sideband contains information, so we need the sideband power to be as high as possible. Okay, so saya menjawab soalan ke yang tanya tadi, pelajar yang bertanya?
Jawab dulu.
Okay, any more question you want to ask, you can ask. Otherwise, I will move to the next slide. Okay. So example 2.10 is the same, same as the previous. You can do on your own. Okay, I will move to the next slide. So advantage of single sideband. Okay, advantage of single sideband either with carrier or without carrier, so no problem. Okay, compared to AM here is the double sideband full carrier, so we need to compare in terms of both. So the first one is power conservation. Okay, so single sideband, you see that all the power previously devoted to the carrier and other sideband can be channeled into the single sideband, producing stronger signal. Okay, further stronger signal and more reliable at greater distance. So in single sideband, actually the amplitude of the sideband is higher compared to the AM, double sideband full carrier. Okay, because we only produce single sideband, and mathematically you will see later that the sideband power are bigger compared to the full carrier, which is good. Okay, we need the sideband power to be as high as possible. Okay, so in terms of power, P total is equal to PLSB or PUSB. PLSB or PUSB. Okay, this is without the carrier component, or with the carrier component you need to plus with the carrier. So we managed to reduce the power, the total power for the single sideband. And then bandwidth conservation, bandwidth is equal to Fm. Okay, bandwidth is equal to Fm, half of the double sideband full carrier. So bandwidthnya adalah separuh daripada double sideband full carrier. Less fading. Fading is the continuous attenuation. Okay, attenuation that happens repeatedly from transmitter to the receiver. That one is what we call as the fading. So in terms of fading, it is less compared to the AM, double sideband full carrier. And then what? Noise reduction. So noise reduction because of less bandwidth. Okay, so since the bandwidth is equal to Fm, okay, that means we managed to reduce the noise power. Remember, noise power is KTB. Okay, if we reduce the bandwidth, we can reduce the noise power, which is good. If we reduce the noise power, that means we can achieve better SNR. Okay, we can achieve better SNR. So what is the disadvantage? Disadvantage of single sideband compared to double sideband full carrier. Okay, so in terms of circuit design, more complex receiver circuit design, which is used to detect for the received signal. Okay, and also add to cost, complexity and size. Okay, so this is in terms of complexity and also in terms of cost. Okay, and then tuning difficulties, requires more complex, precise tuning, need more accurate, complex and expensive tuning circuit. Okay, so these are the drawbacks of the single sideband. Okay, and then what? Vestigial sideband. So vestigial sideband is used for the TV broadcasting. So TV broadcasting consists of audio and video signal, where video signal requires more bandwidth compared to the audio signal. So if we use a double sideband full carrier, it requires 2 times of the message frequency, which is very big. So vestigial sideband tries to reduce the bandwidth produced by the double sideband full carrier, so it allocates more bandwidth to the video and small bandwidth for the audio. Okay, and I want to show, I skipped this one, I want to show this picture for the double sideband suppressed carrier, sorry, for the vestigial sideband. Okay, vestigial sideband, the picture below here, in terms of amplitude, power amplitude here, the amplitude here is PUSB is larger than the PLSB. Okay, in this case the upper sideband is allocated for the video signal, okay, video component, whereas for the lower sideband is allocated for the audio component. And in terms of bandwidth, the distance for the upper sideband, this one is larger for the distance is larger for the for the video signal, which is the upper sideband, compared to the lower sideband, which carries the audio component. So remember, vestigial sideband is used for TV broadcasting, which consists of audio and video signal. Okay, if we use double sideband full carrier, we requires a lot of bandwidth. So that's why it come up with the VSB, vestigial sideband tries to reduce the bandwidth consumed by the full carrier. Okay. So I go back to one slide here. Wait, okay, this one. Advantage of vestigial sideband compared to single sideband. Okay, in terms of sideband filter, design of the sideband filter is simplified. No need to have a sharp cut-off filter. So sharp cut-off filter, we need a more complex circuit design to design the sharp cut-off filter. What is a sharp cut-off filter? Okay, so remember in the for single sideband, so this is okay. So for filtering design, ideally we want a filter that have sharp cut off, sharp cut off like this. This is the ideal case. That means we can take the upper sideband. However, okay, ideally it's like this. So, but in the real world scenario, the cut-off frequency is not like that. Okay, the cut-off waveform is more slope like this. Okay. So if we design a more sharp cut-off filter, it requires more complex circuit design. For this kind of the complexity becomes higher. Okay, and then this improves the low frequency response. And then what? This one, factors to be considered when choosing AM. Okay, when you want to choose either double sideband full carrier, suppressed carrier, or single sideband or vestigial sideband, how you want to choose? Which one is better? Okay, which one is better? Depending on the certain kind of applications. What are the requirements? Okay, so you need to see the bandwidth allocation. If you require less bandwidth, that means you cannot use double sideband. You need to use single sideband. Okay, power. Okay. So power, for power conservation, we can use suppressed carrier or we can use a single sideband, which is better, okay, but better than full carrier. Signal to noise ratio, if the application needs a higher signal to noise ratio, that means we can use a single sideband, for example. Okay, what about complexity and cost? So complexity, if you want a system that has a less complexity, we can use double sideband full carrier. So the full carrier is more simplified circuit compared to the single sideband or double sideband suppressed carrier. Okay, less complex and less cost is for the double sideband full carrier. What about the distance? In terms of distance, you can use the double sideband suppressed carrier or single sideband, which can be we can use it for long distance transmission. Okay, with a good quality of signal. Okay, this one. So now we are in the modulator circuit. So now is the topic on how to generate the AM signal. How to generate the AM signal. Okay. So amplitude modulation voltage is produced by circuit that can multiply the carrier by the modulating signal and then add the carrier. Okay. Remember, this is from the envelope equation. If you remember in the earlier slides. In the earlier slides, remember that VAMT is defined from the VC plus VMT. VC plus VMT, and then multiplied with sine 2 pi FCT. Okay, so it consists of addition process and multiplication process. Okay, ada proses tambah dan tolak. Okay, so the product of the carrier and the modulating signal can be generated by applying both signal to the non-linear components such as diodes. Okay, intermodulation products. So intermodulation products due to the non-linear components. For example, like diode. So it produces harmonics. Okay, it produces what they call the cross product. Okay, it produces the cross product and also the harmonics. Okay, it produces the cross product and harmonics. So the tune circuit filter out the modulating signal and carry harmonics, leaving only the carrier and the sideband. So the block diagram, a simplified block diagram, is like this. Okay, we have the modulating signal and we have the carrier signal. Okay, so we have the analog multiplier. So here is we multiplied this one, VMT, and also the VCT we multiplied, and then we add the carrier component over here. Okay, also we can get the AM. Okay, so we get 3 components. So there are 2 types of AM. There are 2 types of modulators for the double sideband full carrier. The first one, what we call as a low level, and the other one is high level modulators. Low level modulators mean that we generate small amplitude of signal. Okay, we produce small AM amplitude, and we need 1 or more amplifiers before we transmit the signal into the medium. Okay, we need to amplify the signal first before we transmit into the medium. That's for the high level modulator. It produces low amplitude of output signal. For high level modulator, it produces high amplitude of output signal, which is suitable for direct transmission. We can directly transmit the signal. Okay, so let's look at the low level modulator. This one. So this has been come out in the previous semester test and final exam. Pernah ditanya dalam soalan sebelum ini. So we give the actually you don't need to memorize the circuit, because we are not asking about the circuit. We ask you to draw the waveform at a few different kind of location within the circuit. Okay, so you see that here modulating signal and also the carrier, so it will mix. Okay, both signal are mixed together, and then it pass through the diode. Remember, diode only allows current to flow in one direction only, and it prevent reverse bias. So diode is like a switch. Diode here is like a switch. So during the forward bias, what happens is that current will flow in these directions, and it will also what we call charge. It will charge the LC tank circuit. Okay, so this LC tank circuit is like a fast charging battery. Dia seolah-olah seperti fast charging battery. So during the forward bias, this LC tank circuit will charging. Okay, during the reverse bias, LC tank circuit will discharge. So you get the complete AM waveform. LC tank circuit resonate at the carrier frequency. That means at the carrier frequency it will operates, it will resonate, it will function. Okay, in other words, it will function at the carrier frequency. Okay, so in the previous exam, we asked the student to draw the waveform at point A, at point B, and at point C. Okay, and the answer is this one actually, this picture. Okay, so this is actually a simple question actually. Okay, so given here you have the VMT, you have the VCT. Okay, and at point A, when both signal are mixed together, okay, mix is not modulation, mix. Okay, so when both mix, so the carrier follows the shape of the modulating signal like this. Okay, and then what? At point B, right after the diode, so the diode actually will prevent the reverse bias, which is actually here. It cut this this part, the negative part will be cut off. Actually, we have this one. If you see from the above picture, this one has been cut off by the diode. So each time the wave goes to the negative cycle, it will be cut off at point B. Okay, so during the reverse bias, actually the LC tank circuit will discharge. So the LC tank circuit will produce the other half of the signal. Okay, it will produce the other half of signal. This one, okay, so therefore we get the complete AM waveform at the output. Okay, because the LC tank circuit helps to compensate the cut off signal during the reverse bias. Okay, so the answer for the previous semester exam is this one. Draw a picture A, B, and C. That's it. Itu saja. Okay. And then the second type of low level modulator is transistor modulator. So transistor, remember the function of transistor. Transistor is also act like a diode. Okay, transistor also is like a diode, which only allows current to flow in one direction. So transistor is also a switch. And another one is that transistor is have the function to amplify the output. Okay, there are two main things, as a switch and also as amplifier. Okay, so remember about transistor. Okay, if you still remember about how the transistor works, okay, so remember that current flows from the collector to the emitter. Okay, current can only flow from collector to the emitter if the voltage at the base more than the threshold, VB more than the VTH. If VB more than VTH, current can flow from collector to the emitter. Okay, so therefore that means when the base voltage is higher, normally during the positive cycle, and when during the negative cycle, that means the voltage at the base drop below the threshold. So current cannot flows from collector to the emitter. Okay, so you see that during the okay, when the base voltage more than the threshold, that means combination of Vm and Vc more than the threshold, so current can flow from collector to the emitter. At the same time, LC tank circuit will charging. And when the base voltage less than the VTH, V threshold, current cannot flow from collector to the emitter. Okay, what happens is that the LC tank circuit will discharge and produce the other half of the output signal. So the concept is still the same as the diode modulator. Okay, so for this case you don't need to memorize the circuit. Okay, jangan hafal circuit. We are not asking about circuit, we are asking about the concept. Okay, you need to know about how the concept. Okay, so you see that from here, this is a low level. That means after here we need one or more amplifier to increase the amplitude of the output so that we can transmit the signal into the medium at longer distance. Okay, so this is low level. For the high level, there are other two types of high level, which is, so there are two high level modulators. Okay, so before that, in your syllabus, we only give you two types of low level. Actually, in the real world scenario, okay, in the real world, we have more than two of low level modulator. Sebenarnya ada banyak kan. So kita cuma masukkan dua sahaja. Okay. So if you want to see what kind of the other types of low level modulator, you can read the Wayne Thomas's book. There are many types of low level modulator. Various design of circuits. So don't memorize the circuit. Okay. Similar for the high level modulator, there are also many types of high level modulator, but in this notes we only show you two type of high level modulator: collector modulator and series modulator. Okay, so high level modulator produce high amplitude of output signal, which is suitable for long distance transmission. So we don't need to amplify again, it can be directly transmitted to the medium. Okay, so for the first one, collector modulator, see that here we use a transformer and also amplifier to amplify the input message. Okay, so the collector is here. From the collector, so VCC, sorry, not collector, VCC is here, and this current flows in these directions. It will charge the tank circuit. Okay, and it can only flows to the ground if the voltage at the base here is more than the threshold. Okay, when the voltage at the base less below the threshold, current cannot flow to the ground. What happens is that this tank circuit will discharge and produce the other half of the AM waveform. Okay, similar for the series modulator. Series modulator, we use two transistors connected in series. Each transistor is connected to the VMT and VCT. Okay, again, when the current can flow from VCC to the ground, that means both transistors must be switched on. Okay, so current can flows to the ground. Okay, LC tank circuit can be charging, and when either one of these is when both is switched off, that means current cannot flow from VCC to the ground. So therefore, at that time, the LC tank circuit will discharge to produce the other half of AM waveform. Okay. Circuitry of double sideband suppressed carrier. So previously we have seen about double sideband full carrier. How to generate double sideband full carrier? There are low level and high level. Low level we have a diode and also transistor modulators. High level we have the series and also collector modulator. Okay, and what about if we want to produce a double sideband suppressed carrier? Okay, in order to generate the double sideband suppressed carrier, we can use the balance modulator, or what we call as a lattice modulator. Okay, so from this example, I will explain to you how the circuits works. Macam mana circuit ini berfungsi. Okay, so initially you see that okay, from this picture you see that we have the carrier input below here, we have the modulating signal on the left, we have the transformers over here, T1 and T2. Okay, here is also transformer over here, T3. Okay, we have 4 diodes. So this diode will, 2 diodes will switch on at one time. Hanya 2 diode saja akan berfungsi pada satu-satu masa. Okay, so you see that I will draw from here. Hopefully you can understand. So initially the carrier is like this. The carrier polarity is like this. Minus, and the modulating signal polarity is like this. Remember that carrier has a high frequency compared to the modulating signal. That means the carrier will change polarity many times before the modulating signal change polarity. Okay, disebabkan oleh high frequency of the carrier ini, carrier signal telah berubah polarity banyak kali sebelum polarity modulating signal berubah. Okay, so what happened now is, you see that if this happen like this, so current will flow like this. Okay, and you see that this at the coil here, it is a center tap here, center tap at the coil, so that we can divide equally the current. Okay, so the current flows in these directions. So D1 and D2 will forward bias switch on, whereas current cannot flow to D3 and D4. So D3 and D4 will reverse bias switch off. Okay, so current flows in these directions. Okay, and then goes to the output. Okay, similarly, if the carrier change polarity, what happened? If the carrier change polarity, okay, so I erase first. I erase carrier change polarity. If when the carrier change polarity to become like this, positive, negative, that means the current flows into these directions. Current flows in this direction, and okay, it will go to this direction. So D1 and D2 will reverse bias or switch off. D3 and D4 will forward bias or switch on. Okay, so this one, okay, so it will go to the output. Okay, but at reverse, but at different polarity. Okay, okay, so this is the during when the carrier change polarity. So however, when this polarity of the modulating signal change, okay, it will change the polarity of the output also. Okay, so we're gonna see what happened. This picture. So this picture, I take it from the Wayne Thomas's book. I think it's not in the. I think this is not in your notes, maybe. So I take this from the Wayne Thomas's book, chapter 6. Chapter 6. You see that in chapter 6, there's about this balance modulator. Even if you see from the website, from Google, you can also get this picture. So we have here is VMT. Okay, we have VCT, and then this one is VDSB-SC, VDSB suppressed carrier. Okay, so you see that the polarity of the modulating signal, positive and negative, and the polarity of the carrier change, positive, negative, like this. Okay, so what happened? when the carrier is, as I explained earlier, okay, when D1 and D2 switch on, it will produce the output. So you see that the shape of the output follows the shape of the input. Okay, and when carrier change polarity, D1 and D2 will switch off, and instead D3 and D4 will switch on. Okay, and then D3, D4 switch off, and then D1 and D2 switch on. So we have another one, and the rest, okay, until here. Okay, so this is when the phase shift happen, 180 degree, sorry, 180 degree, not percent, sorry, 180 degree phase shift happens. Okay, so when the, sorry, maybe I wrongly, wait, hopefully you are not confused, not here, sorry, 180 degree phase shift is over here. Okay, so over here is message signal goes through the zero crossing, so that means the message signal change polarity from positive to negative, so the output will have a 180 degree of phase shift, so the wave will inverse. Okay, so you see that instead of going down, it will go up like this. Okay, it's not going down, so it's go up. So now the output is inverse polarity of the carrier. Okay, inverse polarity of the carrier. So carrier is negative, it becomes output positive. When carrier is positive, the output is going to be negative. When carrier is negative, the output is positive. So the shape of the output follows the shape of the modulating signal. And then positive becomes negative. Negative here becomes positive. Okay, so the output is not smooth, like it's not a smooth sine wave. In order to make it smooth, we need to use filter. Okay, we need to use filtering technique to make the output signal smooth. Okay, so the picture D here is when we use additional filter to make the output signal more smooth, in term of like this, it's not like this. Okay, so without filter, the signal is in C, and with filter we can make the output signal more smooth. Okay, so the picture D, this picture D is what I have drawn previously. If you remember that I draw like this, the picture that I draw like this. Okay, so this is referring to this one actually. Okay, for double sideband full carrier, and remember this is 180 degree phase shift. Okay, make sure you know how to draw this, okay, so don't use ruler, so make sure you know how to draw this double sideband full carrier, this waveform. And then what? How to generate single sideband SSB. Okay, so previously we have seen a double sideband full carrier. Now we want to see how can we generate the double sideband, how can we generate single sideband. So single sideband, in order to generate single sideband, we can use filtering method and also the phasing method. So phasing method we have asked in the test and exam many times. Sorry, in the final exam many times, a few times. So we have asked this previously. Okay, and the example can be seen from this slide. I will show you later. Okay, filtering method, that means we use filter to filter out the unwanted sideband and only take the sideband that we want only. Okay, either we want to choose a lower sideband or upper sideband. Okay, so you will see later that both of these actually we first generate the double sideband suppressed carrier, then we add another filter to select which sideband that we want. Okay, so let's look at the filtering method. Okay, this filtering method. So you see that the input here is VCT. This is VCT, this is VMT. Put inside the balance modulator. So balance modulator is this one. So balance modulator will do the process of will produce a double sideband suppressed carrier. It will produce double sideband suppressed carrier. So what happened in the balance modulator is like this. VCT multiplied with VMT. Remember, when you multiplied two input, you will produce two sideband, two components. Okay, I have shown you previously. This one. I've shown you in this. This is the equation for the double sideband. Double sideband will multiply two inputs. You will produce two sideband, upper and lower. Okay, and you see that the symbol is X like that. So this is actually multiplication process. So whenever you see the X symbol, this is a multiplication process. Okay. So if you see in other example, this balance modulator, sometimes it will show you in terms of this picture, X like this, round shape with X. Okay, so you produce double sideband suppressed carrier, and then we add another filter to select either one of the sideband. So in this example, it choose the upper sideband and remove the lower sideband. Okay, and then goes through the amplifier to amplify the amplitude, and then we can transmit the signal. Okay, similar with this this is actually filtering filtering method, still filtering method. So this filtering method, picture A, it use a switch, okay, with two different set of filter. Okay, so if we want to select upper sideband, we use the upper sideband filter. When we want to use the lowest, we want to choose lower sideband, we choose the LSB filter. And then frequency translator, and then we amplify the and a linear power amplifier, we amplify the signal and then transmit the signal. And for here, again, this is to produce double sideband suppressed carrier. Okay, so I forgot to say that this is to produce double sideband suppressed carrier. Okay, this round shape with X here to produce double sideband suppressed carrier. Okay, then we have another filter to select. So in this case, picture B, it used two different set of frequency. So frequency 1, it produced a set of upper and lower. Frequency 2 to produce a set of upper and lower. So we can use filter to select either sideband that we want. Okay, mana-mana sideband yang kita inginkan. Frequency translator, and then we amplify the signal and then we transmit. Okay, so these are the filtering method. That means we produce the double sideband suppressed carrier, and then we use filter to select the sideband that we want. And then we can do another process. Either we want to amplify or do another process we can do before we transmit the signal. Okay, and this is the phasing method, and we have asked this a few times in the previous semester. Okay, but there's no solution here in the slide, so I will show you the solution for this example. Okay, okay, so If you don't understand, please ask. So this is also similar with the previous semester final exam question. So this example is similar with the a few semesters ago of final exam. We give this kind of question, okay, where the student needs to find the equations and then find the power and maybe the bandwidth and many other parameters. Okay, so you see that here we have two balanced modulator. Sorry, we have 1 and 2. So please make sure you understand this. Okay, we have two balanced modulator, 1 and 2. Okay, and then we have phase shift, two phase shift over here. We have adder over here, and we have amplifier over here. So remember, balanced modulator do the process of multiplication. Okay, so here we have the modulating signal and also the carrier. So VMT, assume that VMT is equal to sine, Vm sine, so Vm sine 2 pi FMT. Assume that the carrier, okay, assume that the carrier VCT is equal to Vc sine 2 pi FCT. Okay, so both of these VMT and VCT will go through the first balanced modulator. Okay, and then what? Modulating signal also goes through the phase shifter, 90-degree phase shift. What happened if we do 90-degree phase shift to a sine wave? It will become cosine. Okay, it will become cosine. So it becomes like this. So VMT becomes VMT equal to Vm cos. Okay, because sine and cos, the difference is 90 degree. Okay, sine and cos, the difference is 90 degree. Okay, similar with the carrier. So carrier becomes, this one is Vc cos 2 pi FCT. Okay, so in the previous exam we asked the student to find the value of the equation, to find the equation at point A, at point B, at point C, and possibility at point D also you can find. Okay, so at point A, okay, at point A, it is equal to VMT multiplied with VCT. Okay, so it becomes like this. So Vm sine 2 pi FMT Vc, sorry, if you cannot listen to my voice, if there's noise again, you can tell me. Okay, so this multiplied with Vc sine 2 pi FCT. Okay, so it becomes like this. So it becomes like this. Vm Vc over 2. So sine and sine become cos minus cos. Cos 2 pi lower sideband, and then minus Vm Vc cos 2 pi Fc plus Fm. This is the upper sideband. Okay, and then what? At point B, what happened at point B? So at point B, it is again the same process, VMT multiplied with VCT. Okay, so this is become Vm cos 2 pi FMT multiplied with Vc cos 2 pi FCT. So cos and cos, according to trigonometry identity, it will produce cos plus cos. Okay, berdasarkan trigonometry identity, dia akan menjadi cos plus cos. So it becomes Vm Vc over 2 cos 2 pi Fc minus Fm T. So this is the lower sideband plus Vm Vc over 2 cos 2 pi Fc plus Fm T. So this is the upper sideband. Okay. And then what? And then at point C, both A and B is plus. So C is equal to, so I draw here. So at point C, okay, at point C, it becomes A plus B. Okay. So what happened when A plus B? So A plus B, actually we can cancel out. The upper sideband can be cancelled out because plus and minus. Okay, plus and minus. So we add Vm Vc over 2 cos 2 pi Fc minus Fm. So we add the lower sideband. Okay. So what happened? So it becomes like this. Vm Vc cos. So 1 over 2 plus 1 over 2 becomes 1. So Vm Vc cos 2 pi Fc minus Fm T. Okay. This is at point C. Okay, at point C. Okay. So you see that the amplitude is Vm Vc, very big. Okay. So this is at point C. What about at point D? Let's say that the gain is given as, for example, 10, for example. What is the equation at point D? So at point D is equal to A multiplied with C. So that means 10 multiplied with Vm Vc cos 2 pi Fc minus Fm T. Okay, so it becomes 10 Vc Vm cos 2 pi of lower sideband Fc minus Fm T. Okay, so this is at point D. So how can you draw the spectrum? Macam mana nak lukis spectrum? So I teach you how to draw the spectrum. Okay. So let's say you are asked to draw the amplitude spectrum, which is voltage versus frequency. Okay. So you have you don't have the carrier, you don't have the upper sideband, but you have the lower sideband. Okay, and the amplitude is that you have calculated in this example is 10 Vm Vc. Okay, which is this one is the LSB, lower sideband. So from here you can calculate the bandwidth actually. So the bandwidth is equal to Fm. Okay, the distance from carrier. Okay, the distance from carrier, which is Fm. Okay, what about the power? Because previously we asked until power, we asked to draw, we asked to find the power as well. Okay, so for your information, in the previous semester, careless mistake by the student, what they do, they did like this. They assume that the sideband amplitude is Vm over 2, which is wrong. okay, which is wrong. Okay, they assume that this is Vm over 2, which is wrong. So the sideband amplitude is depending on the equation. That's why you need to know the equation first. Very important. Therefore, you can draw. Okay, so be careful. So now the amplitude is 10 Vm Vc. How do I get 10 Vm Vc? Is according to this equation. After I multiplied with the amplifier. Okay, so if you are asked to draw the amplitude spectrum at point D, okay, so this is the amplitude spectrum at point D. Okay, so amplitude spectrum at point C is different. At point C you have Vm Vc. At point A is different. Point B is different. Okay, so now I'm talking about at point D. At point D, the amplitude spectrum is like this. Okay, we have one component, the lower sideband, okay, with the amplitude of 10 Vm Vc, located at Fc minus Fm. Okay, and then what? We can actually find the power. Okay, so how much is the total power at point D? How much is total power at point D? So we only have one component. That means the total power is equal to power of the lower sideband. Okay, which is equal to, in this example, okay, in this example, it is 10 Vm Vc square divide with 2R. Okay, so you will get a value in term of what? Can you see this? Can you understand this? Boleh Ada yang tak faham ke? Anybody don't understand? Maybe I can repeat just few minutes before we close the session. Student, are you still there?
Betul, Doktor.
Okay. Saya risau saya cakap sorang-sorang. Okay. Okay, so do you want to ask a question about this? Because this has been come out in the previous semester. Pernah ditanya. Okay, we asked up to this point, up to find the power. We asked to produce the equation for point A, point B, point C, and then we put amplifier, what happened at the output. So produce the output equation, and then draw the amplitude spectrum. How does the amplitude spectrum looks like? From the amplitude spectrum, I think we asked about the bandwidth. How much is the bandwidth? From there we asked how much is the total power. So you see that the question is in sequence. Okay, we usually ask question in sequence. Produce equation, produce the spectrum, find the bandwidth, find the power, or find other parameters. That's the sequence, you know. Anything else? Anything you want to ask about this? Before we close, we can take the attendance. Kalau ada soalan boleh tanya, saya boleh explain beberapa minit lagi . No question? Sure?
No.
Okay, Doktor.
Okay, that's good. Okay, so that's why in the final exam, in the previous final exam, we are not giving in term of variable like this. Kita tak beri dalam bentuk variable seperti ini. So I just use variable to show the example. Okay, in the real final exam, we give the value. Okay, for example, we give the value for sine for the carrier, for example, like this, 10 sine VCT, for example, like this. So we give the value with 10 sine, for example, 2 pi 1 mega T. For example, this is the carrier, and then the message signal, and then other parameters, we give the value. So in this example, I just show you in terms of variable, but you need to play around with the real values later in the final exam. Okay, and I already explained this. Okay, so next week I will explain about this AM demodulator. Okay, AM demodulator for next week. Okay, so you can take attendance now. I will open the attendance so you can so after you take the attendance, you can go out, you can go to Bazaar Ramadan to buy some foods to breakfast. So okay, so open your QR code reader for section 2. This today is 19. Okay. Okay.
Thank you, Doctor.
Okay, welcome.
Thank you, Doctor.
Welcome. Welcome.
Thank you, Doctor.
Okay, welcome.
Thank you, Doctor.
Welcome. Okay, welcome.
Thank you, Doctor.
Okay, welcome.
Thank you, Doctor.
Welcome.
Yes, Doctor.
Okay, welcome.
Doctor,
Yeah,
just a minute. I want to scan.
you can scan. What's your name?
Muhammad Abdul Karim.
Muhammad Abdul Karim Abdul Rahman. Okay, done.
Okay, thank you, Doctor.
Also muted.
Doktor, saya pun tak boleh nak
Okay,
scan.
one by one. What's your name?
Nurul Amira.
Nurul Amira. Okay, jap. Nurul Amira Amir.
Yep.
Okay, done.
Terima kasih, Doktor.
Usama, Doctor.
What's your name?
Usama, Doctor.
Usama. Okay, done.
Thank you, Doctor.
Okay, welcome. Who else?
Doctor Muhammad Joki.
Jokri.
Yes.
Muhammad Jokri. Mana Jokri?
Nombor 11.
Mana Jokri? Tak ada pun.
Nombor 11.
Oh, 11. Okay, done.
Thank you, Doctor.
Nombor
Okay.
15, Doktor.
Who else?
Nombor 15. Amir Amri Adam.
Muhammad Amirul Amri Adam.
15.
Okay, done.
Thank you, Doktor.
Okay, welcome.
Muhammad Daniel Putra.
Daniel Putra. Daniel Putra. Okay, done.
Alright. Thank you, Doctor.
Okay, welcome.
Doctor, nombor 20. Muhammad Hamshari Hamzan.
Hamshari Amizan. Okay, done.
Thank you, Doctor.
Okay, welcome. Who else? Yang lain ni dah ke? There's a Sundus. Okay, Sundus attend the class. Firdaus. Firdaus bin Muhammad. Okay, Firdaus also attend the class. Okay. So who else? Sundus done. Firdaus, Fauzi. Okay, done. And another one is Alif. Alif's not attend. Okay, so I will stop sharing. Alif. So Alif baru nak masuk ke apa ni? Terkeluar. Okey, saya tick attendance. Okey, done. Saya dah tick attendance untuk Alif. Okey. So that's all for today. Okay, welcome.